Welcome everybody on our seminar of quantum information and quantum computing seminar. Today our guest is Sophia Denker from Siegen University in Germany, and the title of her talk is Chiral Symmetries of Multiparticle Entanglement. Sophia, please.
Yeah, thank you for the introduction. Today I will present chiral symmetries of multiparticle entanglement. And this is a joint work with Satoya Imai, who is now in Florence, and my supervisor, Ottfried Güne. Okay, so let us start considering two qubits. So if we, for example, consider these two Bell states, the upper one, you can see that if I apply a flip operator to this, it remains unchanged. So it's the same, which means we call this a kind of state symmetric. And in the second example, if we apply the bit flip here, we get a minus sign, which means the state is antisymmetric. And if now we consider free particles, we can have the same things, like we can have symmetric states that are invariant under any exchange of two particles. And we can have antisymmetric states that get a minus sign if we exchange two particles. But you can see I left some gap here because there actually also occurs another symmetry, which we call now chiral subspaces. This is denoted by J and J bar for now. And within the talk, I wanted to present you these chiral subspaces. So we will have a look how the bases operate, the basis vectors look like. We will find that they are highly entangled. And also we will see some operators connected to structure constants of Lie algebras that turn out that these eigenvectors are also living in these chiral subspaces. Okay, first let me recap the entanglement structure. So for free particles, we have this orange area here, which are all the fully separable states, or states that can be written as a tensor product of Alice, Bob, and Charlie's particle. Then we have the biseparable states, which are all the states that can be written as a tensor product of Alice's part and Bob and Charlie's part, or all the other possible bipartitions and convex combinations of this. And then we have the genuine multipartite entangled states that cannot be written in any of the previous forms. And if we want to know how entangled a state is, there are several measurements of entanglement, and one is the geometric measure of entanglement, which is given by 1 minus the identity over the maximum overlap of that state with the closest product state. So if we have some state psi and we want to know its geometric measure of entanglement, we have to find its closest pure product state pi, and then the distance is just a geometric measure of entanglement. For example, if we consider this state phi prime, which is a biseparable state, we see that this is closer to the set of separable states, which means it is less entangled with respect to this measure. Okay, so now let's start considering three qubits. And what is important to understand these chiral subspaces is the cyclic translation operator, which we call T. And if it acts on a ket state ijk, we get back chi ij, so the cyclic translation. And here we consider, so this blue circle, I drew it as denotes the Hilbert space. And in the qubit case, we have symmetric subspace and the chiral subspaces. And now if we apply the operator T to the symmetric state, we'll find that this is invariant under this operation, which means it has the eigenvalue 1. But we can find that T cyclic has two more eigenvalues, which are given by the phase omega, which is e to the I pi over 3. And these are the the eigenvectors belonging to these eigenvalues are these chiral symmetric chiral symmetric states. So we can have either the eigenvalue omega or the eigenvalue omega squared, which is also the same as the complex conjugated of omega. And yes, so since these states also occurred in the paper of Venn, Wilczek, and C, we following their notation, we call these states chiral symmetric. Okay, now that we saw this chiral symmetric space, I wanted to show you how the projectors on these subspaces look like. So the symmetric subspace, we can, up to normalization, write it as the sum of the identity, the cyclic translation, and the anticyclic translation, which is the Hermitian conjugate of the cyclic translation. And then for the first chiral subspace, we can have the same operators, but with different coefficients. So we have the identity plus this phase omega, the cyclic translation plus omega square anticyclic translation. And for the anti-chiral subspace, we have the same, but the two coefficients are interchanged, which means this is the complex conjugated of the first chiral subspace. And
Sophia, can I have a question now?
Yes, sure.
So this is for qubits. This permutation operator is now we are talking about qubits, right?
Sorry, about.
So what's the
yes.
local dimension of the system?
Yeah, I know qubits. So the local dimension is 2, and there are 3.
Okay, but then I don't understand why the permutation operator has eigenvalues omega and omega square.
Sorry, can you repeat?
So I don't I don't understand why the permutation operator, the T operator, has complex eigenvalues, let's say, because I used to think that it has plus minus 1 eigenvalues only. Okay, I'm wrong. Okay, sorry. I confused it with
okay.
some other operator. Okay.
Okay.
No problem.
Okay, no problem. Okay, so yes, we can see that these operators sum up to 1 to the identity, which means we can write the subspace in this form. And yeah, now I told you before that we found that these subspaces are highly entangled. So yeah, let's take a look at the geometric measure of entanglement for these states. And okay, so here the notation is a bit fishy, but I meant we consider the geometric measure of state psi that is either in the chiral subspace J or J bar. And the upper bound of this geometric measure, we can write it as 1 minus the maximum expectation value of the projector of one of those two states, of both of the two states. And then one can show that this is the same as taking the minimum of the minimum expectation value of the symmetric projector, which we can do because all these projectors here sum up to the identity. And this term, after some algebra and calculations, we find that this is always bigger than 5/9. And the 5/9 is the highest geometric measure of entanglement one can get in 3-qubit states. So we know that this state is highly entangled, or all these states in the subspace are highly entangled. Then now we want to consider this operator W, which we can write as a sum over the epsilon tensor and and the tensor product of Pauli matrices, sigma I, sigma j, and sigma k. And yeah, this operator has some properties. Like first, the sum of its eigenvectors coincide with the states that live in this chiral subspaces. And it is useful for entanglement detection. So we can use it as an entanglement witness by finding, like, if we consider the maximum expectation value for all separable states, we get that this is upper bounded by 1. For all biseparable states, we get it is upper bounded by 2. And the algebraic maximum for all quantum states is 2 times square root 3. And we find that this bound is saturated by our chiral vectors, by the chiral eigenvectors. And yes, since these are nice properties.
Sophia, can I have another question? So what's the dimension of this chiral subspace?
In this case, the dimension of like one chiral subspace, it grows with the order of the local dimension to the 3.
But if you have 3 qubits, so what's the dimension if you have 3 qubits?
For 3 qubits, it's 8.
No, just the whole Hilbert space, but I'm talking about the this chiral subspaces, the eigenvectors of the T operator.
I'm sorry, I wrote it down somewhere. But we have. No, I think we had. No, for 3 qubits, the subspace is 2. I'm sorry. Yes, I was already thinking in qubits.
Okay,
yes.
thank you.
Okay, and yes, so now we want to generalize this to higher dimensions. Okay, so if we consider, yes, in order to generalize the operator W to higher dimensions, we consider that the epsilon tensor can also be interpreted as a structure constant of this Lie algebra. Yeah, it occurs in the definition of the commutator of the Pauli matrices. And so we can express also the epsilon tensor as trace of sigma k and the commutator of sigma I and sigma j. And if now we want to generalize this structure constant in higher dimensions, we can replace the Pauli matrices by some Hermitian traceless d by d matrices, which, for example, Gell-Mann matrices. But later we will also see that we can take any orthonormal system of matrices that fulfill these properties. And then we can write our structure constant in higher dimension, which is given by minus I over d squared and the trace of lambda I and the commutator lambda j and lambda k. And if we now replace everything in the previous operator, we have generalized this operator to any arbitrary dimension. And yes, and this operator has also some nice properties. For one thing, I already mentioned that it is independent of the choice of the matrices lambda, as long as we also adapt always the C according to its definitions. But then no matter what basis one chooses here, we'll always end up with the same operator W. From this, it also follows that the operator is invariant under unitary transformations. And if we have this property, we can apply the Schur-Weil duality, which means that any U invariant operator can be written as a linear combination of permutations. And if we do so with this operator W, we find that this is a special case of the operators that were considered in the paper by Eggeling and Werner. And so, as well as there, also in our case, we can use this operator as an entanglement witness. And here I plotted the dimensions versus the bounds for separability, biseparability, and the quantum bound. And we see that the fully separable bound scales with local dimension over 2, the biseparable with the dimension, and the quantum bound with d square root 3. And we kept for qubits the numbers I mentioned before. So we see this is the true generalization of this operator.
Sophia, can I have a question?
Yes.
So how do you compute these bounds? Is it easy to see?
No, it was a bit hard. So first we did it just numerically, but then we also found an analytical proof. But yeah, this was pretty technical.
Okay.
Okay, but as I said, the last property is that the eigenvectors are living also in this chiral subspace, and these are again the eigenvectors that saturate the quantum bounds here. And now we can write down the UUU invariant chiral subspace, where now I write down the the basis vectors that span this space J. But for getting the space J bar, we would just take the complex conjugate of this J space. So there are 4 types of basis states. Like the first 2 types, they only depend on I and J, and have the form omega iij plus omega squared iji plus jii. And the second, yeah, it looks omega ijj plus omega squared jji plus jij, which is yeah, permutation and then interchange I and j, where we define that I is always smaller than j. And the second type depends on 3 coefficients. So we have omega ijk plus omega squared kij plus kij, so always the cyclic permutation of the cats. And here we denote or we define that I is always smaller than j is always smaller than k. And the fourth type of these vectors is given has the same form as the third, but we interchange k and j. And yeah, here one can count that these yeah, how many basis vectors we have. And that's what I meant before. I was thinking about this subspace for local dimension 3. We have 8 of them. And yeah, but the order grows with local dimension to the 3. And now, as I said before, we also want to check here that these states are highly entangled. And we find for the states of the first 2 types that the geometric measure is always greater or equal 5/9 again, which kind of makes sense because this is like the qubit case, but yeah, implemented into 3 dimensions. Yes, and then for the other 2 types, which depend on 3 coefficients, we find an even higher geometric measure, which is 6/9, which also coincides with a geometric measure of some absolutely maximally entangled states. And yes, so this is the unitary invariant chiral subspace. But we can also have a further subspace, which we will see is even higher entangled. So as a reminder, I put again our structure constant, which is yeah, depends on this trace of lambda I and lambda j, lambda k. And we can see that we can also write this trace expression as the trace of I, the tensor product, and the commutator times the swap operator. And where the swap operator just swaps two qubits. And it's proportional to the maximally entangled state, partially transposed. And as I said before, this belongs to the unitary subspace, unitary invariant subspace. This is also since the swap operator is unitary invariant. And if we now apply the partial transpose, we have that the swap operator partially transposed is proportional to the maximally entangled state, which means we would replace the swap operator here by the maximally entangled state projector, which makes our, if we plug this in back to the state operator W, makes it inheritate this property that it's now orthogonally invariant. And by replacing these, we get now an operator W tilde, which is invariant under orthogonal transformations. And yes, and this operator, as the operator before, if we take a look at its eigenspace, we find that these eigenvectors coincide again to our chiral subspace. I put it now in quotation marks because it doesn't have this W symmetry anymore. But it's like comes from the same other properties. And I want to show you how these states or basis states look like. The first one is we have kept 0, 0, 0 plus some complex number omega d. Plus some complex number omega d, I0, where the I is summed over 1 until d minus 1. And the complex conjugate of this omega times I0i. And this omega d is now different from the phase before. It's a complex number that depends on the dimension d. And having written down this first state, we can construct a further state by applying this operator X, which is also a generator of the Heisenberg-Weil basis. And it acts on a ket ijk and gives us I plus 1, j plus 1, k plus 1 modulo the dimension. And by this, applying it always n to the n minus 1 times to the first basis vector, we can construct the whole basis, which means that we always get d vectors, which shows that this chiral subspace J and also J bar have the dimension d. So here I plotted the geometric measure of entanglement versus the local dimension, so the lower bounds of the geometric measure of entanglement, where we can see, for one thing, that the unitary invariant space is always constant with respect to the dimension, and the OOO invariant grows with the dimension. And also we see that it's way higher than the unitary invariant subspace, which for one thing, the reason could be that also its dimension itself is smaller. Yes. And the other thing we see is that for qubits, the two bounds coincide. So for qubits, we have the same geometric measure for the orthogonally invariant and the unitary invariant subspaces. But this means, or we could also show that they are local unitary invariant. So if we take a vector in the 3-qubit vector in the OOO invariant space, we can find local unitary transformations which gives us the vector in the unitary invariant space. Okay, and with this, I'm already at the end. I want to quickly summarize what we saw. So yeah, we saw that we not only have symmetric or antisymmetric subspaces, but we can also have these chiral symmetries. We see that these chiral symmetric subspaces are actually highly entangled subspaces. And we saw that we can construct operators using structure constants of Lie algebras, whose eigenvectors live in these highly entangled subspaces, in these chiral subspaces. And further, we saw some orthogonally invariant subspaces, which are even higher entangled. And as an outlook, we are currently working on having a look what are these subspaces useful for. For one thing, we can use them to estimate further entanglement measures and entanglement properties. But also, since they have this high geometric measure of entanglement, they are probably useful for quantum secret sharing because since they are highly entangled, they are hard to distinguish locally. And yes, with this, I'd like to thank you. And yeah, I'm happy for further questions.
Thank you very much. Do we have any further questions?
Well, I can start.
Please go.
So are the subspaces generally entangled? I mean, in the sense that like all the vectors from the subspace are generally entangled?
You mean in the
chiral subspaces? For instance, if you had this construction with how it was like 3 vectors or something before.
These ones.
Oh yeah. Okay. Yes, this, for instance, this one. So the first 2 vectors, so they are generally entangled, but then if you take any linear combination of them, is this combination generally entangled as well?
Yes. So this upper bound is valid for and also for the
combinations. Yes. Okay.
And
is this,
yeah, in this.
Okay, continue.
Yes. So in the unitary invariant case for qubits, also the geometric measure is always the same. It's always 5/9. But in the higher dimensions, this is just the lower bound, so it can also increase if we take linear combinations.
Okay, and what's the maximal value for 3 qubits of this geometric measure of entanglement?
It was
5/9.
Yes.
Is it the maximal value of 5/9?
Yes, if I remember correctly, it's the same as for the W state.
Yeah, because these are the W states, right? Up to the the faces, because the faces are different here, but I mean they look like W states. So it means that every linear combination of these 2 states is a W state again.
In the qubit case.
Yes, in the qubit case. Okay. And is it always true that the subspace is generally entangled, like in any, like with any local dimension and so on, any number of parties and?
You mean for more parties, we only roughly consider.
So
we
okay.
focus
So like for the higher dimension, they're always.
Yes. So with respect to the geometric measure, it's always true. So what I plotted here, it's always the lower bound of the geometric measure.
Okay. Okay, thank you.
On this.
But I can have another question.
Okay, please go.
Okay, so like because if you have a subspace, now we can define mixed states acting on those subspaces, right? And have you checked whether those mixed states can be PPT entangled or something? These kind of things?
No, I think we haven't checked this.
Okay. Because then you would have like examples of mixed states that are perhaps highly entangled and are PPT entangled at the same time. So
yeah, no, I think we didn't, but it's maybe we should check it.
okay, thank you.
Thank you.
Do we have any other questions from the rest of the audience?
Okay, maybe the last one.
Okay, please ask the last one.
So you have studied two symmetries, right? The unitary and orthogonal, and are you going to study some other symmetries?
So you mean
Because
beyond unitary?
Beyond orthogonal, let's say.
Like once we were also thinking about this rotational invariant, which like only have
Yeah,
8.
Mm-hmm.
But if I remember correctly, it turned out that they were unitary, equivalent to the orthogonal case or to the unitary case.
Okay,
I have to double check.
To be honest, I'm not so sure because there were these results by Heinz Peter Breuer, where he showed that in some cases, if you have SO3 invariant states, then there is no PPT entanglement or something like that. Whereas I think that if you have O times O invariant states, you can have PPT entanglement. But I don't remember now. So it might be that there is some difference.
Which paper was this?
So he has, okay, what was the, in 2004-5, he has 2 papers, or 3 even, about SO3 invariant states, but bipartite ones. And in one of the papers, he proves that if you have 3 times, one dimension is 3, the other one is n, and if n is odd or something like that, then there is no PPT entanglement in such states. So for instance, if you have 3 times 3 states which are SO3 invariant, there is no PPT entanglement. And I think that in the paper by Werner and Vollbrecht, they prove that if you have O times O invariant states, then you can have some PPT entanglement, right? Well, I'm not so sure now, but O times O invariant states.
I will check on this. Thank you.
Okay. Thank you.
Thank you very much. I cannot see any more questions or comments. Sophia, thank you very much for your presentation, and thank you for all our guests for today. See you next time. Thank you very much.